If you're forgetting to do calculus in the calculus, then maybe you save it for another day, right? All right, we're on example 4 then. Find the volume of the solid obtained by rotating. So it's the volume of solid of rotation or revolution. We're taking the region then bounded by x cubed, y equals 8, and x equals 0 about the y-axis. Ooh, man, these are good problems. I wonder who came up with these. All right, so x cubed, we got to graph him first. I'll use pink. He's our disco graph. Looks like that. Y equals x cubed. Y equals 8. I'm just going to draw that horizontal line up here. And x equals 0 is the, of course, y-axis. So the region that's contained by all of them is this little region here. Now it tells us that we're going to rotate that thing around the y-axis, which is still a line, but it's a vertical line. And because we only have one method at our disposal, which requires us to slice it perpendicular to the axis of rotation, since we have a vertical axis here, we've got to slice it how? Horizontally, yeah. Now in the future, as I mentioned, you're going to have a method that accommodates a slice that would be the same direction as the axis, but we're not quite there yet. So a horizontal slice would be dy, and that's going to give you your radius as a function of y. So just as before, if we were doing this with area, we need to integrate from low to high. So that's going to be from y equals 0 to y equals 8. And we need to be able to solve our equations for x. So if y equals x cubed, then x equals the cube root of y. So that's the equation on the right. And the axis itself, x equals 0, is on the left. So we're ready to go. In this case, if you sliced it, if you wanted to see what the three-dimensional object would look like, it would look like this. It would kind of be another disk, but facing upwards. And if you sliced it all the way through, this time, your cross-section would look something like this, dy. But it's still a round face. So we're still going to do pi r squared, but this time dy. So volume, VOL, is pi, sum of the infinitely thin slices from y equals low to high, which is from 0 to 8, of r squared dy. And now r squared is not top minus bottom, but rather right minus left. And so the curve on the right is the cube root of y minus the curve on the left is really the axis of rotation, which is x equals 0. So again, that communicates your method there. So if you want to evaluate this thing now, we'll simplify. That's pi from 0 to 8. That's really y to the 2/3 dy. So I'll work here from right to left. So pi goes for the right. The antiderivative becomes y to the 2/3 plus 1, 5/3, oops, with the 3/5 out front. And we evaluate it from 0 to 8. So now our coefficient is 3 pi/5. And we'll plug in the 8. So we get 8 to the 5/3 minus 0 to the 5/3. And there's a numeric answer. Well, we'll keep going because we're curious. Let's see, 8 to the 5/3. Do you want to go 8 to the 5th first and then try to take the cube root? Me neither. So how about the cube root of 8? That's 2, and 2 to the 5th is 32. And of course, 0 becomes 0, so we get 32. And 32/5 doesn't divide out, so we're just left with 96 pi/5. It's a positive number, cubic units. You don't have to put cubic units. But it is a three-dimensional volume. Nice. So it doesn't matter now if the axis is vertical or horizontal, if it's the x-axis or the y-axis or some other axis that's the line. Right now we have to slice it perpendicular to the axis. But what's happening in all of these examples we worked so far is our cross-section has been uniformly dense. It has been a solid disk. But that's not always the case. So look at example 5. It says, what if we were to take the region from the previous example? That would be this right here. Let me kind of copy this and get rid of the clutter. What if we were to take that same region, get rid of that, get rid of that, get rid of that, It might be worth just redrawing it. Yep, sure is. All right, so x cubed, pink, that's what I used. And y equals 8 and 0. All right, so here's the same region. What if we took that region now, and instead of rotating around the y-axis, we rotated around the x-axis? Well, the x-axis is a horizontal line, and now we'd have to slice it how? Vertically, and that'd be back to dx. But what's interesting about this example is if you envisioned rotating it around the x-axis and seeing what the shape looked like, you can reflect the line y equals 8 down here to negative 8, and then mirror that like that. It's going to have something like this, and like that, and this will also be solid. Okay, and it'll be solid through here as well. So when you slice it, it's going to look kind of like maybe a decorative shot glass turned sideways. And when you get older, you'll hear about these things called shot glasses. They're used to measure what's called alcohol into drinks. And this would be kind of like perfectly cylindrical on the outside, but it would have this convex interior. But if you were to slice all the way through, you wouldn't have any more a disc, would you? If you looked at the cross section and you looked at it face on, it would look like a pineapple slice instead of a tomato slice, right? Or it would look like this. It would look like that. Here's the axis of rotation. It would be like a disc with a hole in it, okay, which we call a washer. And by washer, we don't mean like someone who washes things, but rather like a flat washer, as opposed to a cut or a lock washer. A flat washer. Well, can we still use the disc method then?
Yes, we just subtract the cylinder.
Very good. We can modify our disc because really all a washer is it's the hole with a W minus the hole with an H. So it's the W hole minus the H hole. And that sounds bad. Okay? H hole. Like F hole, right? It's the whole thing minus the void that we drilled out. So it's really just a disc minus a disc. That's all it is. All right? So let's figure out what we would do. We would take the volume of the W hole minus the volume of the H hole for either one of these slices. Well, that's going to be pi big R squared dx. I'm going to use big R to represent the radius of the past, okay? It would be the big radius. Big R for big radius, are you okay with that? Minus the volume of the void, which will be another cylinder, pi little r squared dx, okay? And so I'm going to call little r the radius of the void. So that's the idea, volume minus volume, pi r big R squared dx minus pi little r squared dx. Well, what do you see is common in those two terms? There's a pi that's common, so we could factor it out. And there's a dx that's common, which we could factor out. So let's factor out the pi on the left and the dx on the right. And now we have the volume of that individual washer. And all we have to do is add those up from A to B. And guess what? We get the volume. So this becomes known now as the washer method, which is still perpendicular to the axis of rotation, but now we have to come up with a new word. So not perpendicular, but perpenwascular. That's right. It'll grow on you. It hasn't found its way into any kind of dictionary yet. Perpens. Yeah. All right, so let's go ahead then on our graph. And again, you don't have to draw the part below the axis. Sometimes it can kind of obscure what we're doing. All right? But remember that your radius has to come from an axis. If you don't have an axis, you don't have a radius. So here's what I always want you to do. I always want you to draw your radii. starting from your axis, because I have the profound belief that if you can draw what the radii are, then you can find their equation. All right, so from the axis, which is the x-axis, to the first curve, that should be little r. Because you hit the first curve, it should be smaller. And from your axis to the outer curve should be big R. Those are your two radius of rotations. And they're both variables, right? As big R decreases, little r increases, and versa versa. So here we go. The volume now by the perpendicular method, VOL equals the sum of the infinitely thin slices from x equals 0 to x equals, crap, we haven't found it yet. We better do that. We found the y value. We didn't find the x value. So let's go ahead and set them equal to each other. We got x cubed is one of the y functions, and y equals 8 is the other one. That's when x equals 2, all right? All right, so now we have our intervals integration. So what goes out front for both the disk and the washer method? Pi. Okay, pi times the sum of the infinitely thin slices from 0 to 2 of beefy brackets, because now we're going to have two terms, sorry. So here's what I do each and every time. Watch this. The cadence works beautifully. Big R squared minus little r squared. Close beefy brackets dx. Big R minus little r. Big R squared minus little r squared. Guess what the temptation for students to do is? No, that's actually not the most common error. But that could be problematic. A lot of students want to subtract the radii and then square it, rather than square the radii and then subtract. And that's not the same, is it? So if you say big R squared minus little r squared, and you'll hear that the day of the AP exam, right, Megan? Perpendicular and big R squared minus little r squared, you'll know to subtract them after you square them. Okay, so now that we've drawn what they are, it should be pretty easy. What is big R? Well, it's top minus bottom. It's 8 minus what? 0. So you really don't even need calculus for that part because it's a smooth cylinder all the way around the outside with a constant radius. So we'll just might as well use calculus. Might as well show off. And then little r is top minus bottom, which is x cubed minus 0. So the bottom curve in both of these was the axis. The axis. Now that's different than what we did in 6.2, because in 6.2 we would be writing this as h of x, and it would be 8 minus x cubed. But that's not how we do the washer method. It's 8 minus 0, axis on the bottom, and little r minus 0, axis on the bottom. We square them and then subtract them. So this now is your setup, and then it's just a matter of evaluating it, which I guess we could do. Let's figure it out. Pi, integral from 0 to 2. If we simplify now, we get 64 minus x to the what? 5th or 6th? 6th. Good. dx. So if we integrate, we get 64x minus 17x to the 7th from 0 to 2. And we get pi, we get 128 minus, let's see, what is 2 to the 7th? 128 sevenths? 32, 64, yeah. And then when I plug in the bottom, I still get 0. So there it is, whatever the answer comes out to be. A lot of these end up being calculator questions. And if they're not going to have huge numbers like that. But whether or not it's a calculator question, you get 2 checks right here. That's your integral setup. And then from there, if you just type it into your calculator, it's probably worth simplifying before you go to the calculator. 64 minus x to the 6th. Just don't forget your pi. If you did it on the calculator, you'd go pi, math 9, 64 minus x to the 6th dx, and you get your 3 decimal approximation. But anyway, there it is by hand. You get a point for the antiderivative as well if you did it by hand. So it's the setup that's really important. So we probably won't even be evaluating them after this. All right, so how do we know that that was going to be a perpendicular method?
It had a hole.
It had a hole, right? Our area was not flush up, butted up against the axis of rotation. That's an easy way to tell. Your axis is x equals 0, and notice your region is not abutted up to the axis. So you're going to have a void. And so you're going to have 2 radii. But we knew it was still a washer modification or a disk modification because our slices were what in relation to the axis? Perpendicular, or in this case, perpendicular. So here's the summary of the washer method, perpendicular. Big R squared, just like before, but now minus little r squared. And we want to do it as a single integral. Big R squared minus little r squared, pi, out front. Don't forget the pi. Don't forget the pi. It goes out front, right? Life's too short, eat pi first. Put it out front. All right, so here we are, example 6. The region in the first quadrant enclosed by the y-axis and the graphs of cosine and sine is revolved around or about the x-axis to form a solid. Find its volume. Worded slightly differently, but still the same thing. Find a region, rotate it, find the volume. Step 1, identify the region. Okay, let's see, the y-axis. I know what that is. That's this guy here, y-axis. Cosine. The pre-calc kids in the last 2 days have met, finally, Sahala and Chala. No, not until this week, Sahala and Chala. And then, of course, they're Bizarro twins, negative Salaha and negative Klahal. Anyway, we're going to graph Chala. It looks like that. And if you want to do it over here, that's fine. So there's the graph of cosine. And then sine would be this one. Something like that. So the region, there's lots of regions, right? And I should probably specify, it says the region in the first quadrant. There are infinitely many regions in the first quadrant. So I should say the first positive region in the first quadrant. So it's that. That's what I'm intending. Not this little partridge-looking thing over here or above, because they're going to intersect infinitely many times. So let's just agree. I need to reword the question to avoid some confusion. But let's say it's that region right there. So we're going to take that region and we're going to rotate it around the x-axis. So we'll do that. Now the x-axis is horizontal, so at this point we're committed to slicing it how? Vertically. And if we had to choose to find the area, we would choose a vertical slice anyway, because you could do it with a single equation. From left to right, it's always going to be cosine on the top and sine on the bottom. Whereas if you slice it horizontally, gross, you would need 2 setups because the right curve changes. And then you would need arc sine and arc cosine. So anyway, this works out great. So we're going to integrate from left to right. Here's the slicing method. From 0 to what? Let's say it's no calculator. I want to know where sine and cosine first intersect. Pi fourths. That's going to be the first time on the unit circle where they have the exact same ordered pair. Square root of 2 halves, square root of 2 halves. Good. All right, so now is this going to be a perpendicular or perpenwashular method? It's a washer. Good, because our axis is the x-axis, and it's not flush up against the x-axis. So from the axis to the first curve is little r, and from the axis to the second curve is big R. And if you could draw it, you can write the equations. I have faith in you. So here we go. The volume is, what goes out front? Pi. Sum of the infinitely thin slices from 0 to pi fourths. Beefy brown brackets. And here we go. Big R squared minus little r squared dx. So I always do it as a 2-step process. And then I come back and I look to see what big R is. Big R, the curve on top is cosine, and the curve on the bottom is the axis. So it's cosine of x minus 0. Cosine x minus 0. And then little r is sine on the top. Axis equals 0 on the bottom, so it's sine minus 0. And congratulations, you get yourself 2 of the 3 checks. One for the integrand, typically, and one for the intervals of integration with the correct coefficient pi out front. Now, if we were going to put it into the calculator or do it by hand, we would probably simplify either way. So that ends up being cosine squared minus sine squared, which I think I'm feeling a double angle identity coming on. If I had to do it by hand, we would have to either use the power reducing identity for both cosine and sine, or what is this equal to? It's not pop-up head, it's cosine of 2x. Yeah. So here's one of those times where if we didn't have a calculator at our disposal, knowing that identity makes it easy. All right, so pi goes along for the ride. Cosine has an inside function of 2x, whose derivative generates an unwanted 2. So we'll have to have a correction of a half. And now what is the antiderivative of cosine of blob? Sine of the blob, 2x. And we evaluate it from 0 to pi fourths. So the pi is still out there. The 1/2 is a correction. Yes, this is a good type of candidate for a no calculator free response question. Yeah. So pi halves, again, I like to pull my coefficients up front, and I get sine of 2 times pi fourths, which is pi halves, minus sine of 0. And I guess if this were a free response, is that an okay place to stop? Yeah, because both sine of pi halves and 0 are defined. But then for a non-calculator multiple choice question, that wouldn't be there. So sine of pi halves, of course, is 1, and sine of 0 is 0. So the final answer ends up being pi halves cubic units. We didn't even draw what the shape looks like. But if you did, it's kind of cool. It would look something like this. I don't know, maybe kind of like a napkin ring or something. Not a napkin ring because it's solid. It would be, I don't know, some rounded mound on the outside all the way around. Some kind of dish, maybe a dog dish. That makes a pretty good little dog bowl right there. Yeah, it's a good dog bowl. Not bad. So we just found the volume of the dog bowl to be pi halves. Now that's not the capacity that's carved out. That would be how much the dog bowl could hold in water or food. But we found the actual, the bowl itself had a volume of pi halves cubic units. So much fun, isn't it? Volume of solids of rotation. Yeah, I like them. They're good. All right, so this is just a summary of what we did. If you want to read it, feel free. Here's a common error that I mentioned, big R minus little r squared. If you do big R minus little r, that's the same as h of x from 6.2. And we don't want to do that. If there's a void, the axis always has to be one of the curves in each of the radii. So you square them and then subtract them. Don't subtract them and then square them. All right, so the second word of the day is perpendicular. All right, so let's put it all together. Example 7. Find the volume of the solid when the region enclosed by these two curves is rotated about the following axes. X-axis, y equals 2 and y equals -5. Then the y-axis, then x equals -1, and then the line x equals 17. What the? That's a lot of different volumes, okay? Same region, though. We're just taking it for a spin around the different axes each time. We won't do the work. We'll just do the setup, right? Yeah, I like that. We could say we did it and still not do it, and then no one would be any wiser. So y equals x and x squared. Let's identify the region. X, y equals x, and then x squared. Kind of like the quiz we just took, except with x instead of the square root of x. And so the region itself is just that little sliver right there. Now we're going to need this graph multiple times, so I'm going to go ahead and copy it. And might as well just paste it in here for now, because we're not going to finish all these, and I want it there tomorrow when we pick back up. Paste, paste, paste. When y'all were little and y'all had to get school supplies, it usually called for glue. Did your mother ever buy you paste instead? No, paste. It comes in a tub and it's screw-on lid and there's a stick in it. And so when everyone else had Elmer's glue, I had paste, and I had to smear it on. Yeah, and then you're always tempted to eat it, because it's on a stick, and you're like, mmm. Now it's back before paste was non-toxic. So anyway, another story from my childhood. That's why I am the way I am. It wasn't all ROSPA damage. Some of it was paste. Okay. So we're rotating this around the x-axis. And we still only have one method, right? We still only have the perpendicular / perpendicular. So I'm going to have to slice this half. My axis is horizontal. Vertical. So is it going to be a disc or a washer? A washer. So from the axis to here is little r. From the axis to the outside is big R. Let's go ahead and get our points of intersection. It's 0, 0, and what? 1, 1? Yeah. So that's going to be the same. So we're always going to either integrate from left to right from 0 to 1, or in this case from low to high from 0 to 1. That's kind of nice. We don't have to think too hard about that. But here we go for this one. The volume is going to be what goes out front? Pi, the sum of the infinitely thin slices from left to right, which is from x equals 0 to x equals 1, beefy green brackets, big R squared minus little r squared, close beefy green brackets dx. And now we'll come back with maybe a different flavor. What goes good with green? Grape. Beefy brown, okay. So what is big R? X minus 0. And lil r, as he likes to be called, lil r, x squared minus 0. Yep. And there's your two checks. With or without a calculator, this is a pretty easy one to evaluate. X squared minus x to the fourth. You're done. We're not going to evaluate it, okay? Letter B, around the line y equals 2. Well, they intersect right here at 1, 1. So the line y equals 2 is a horizontal line that's up here. Oops, up here. Y equals 2. All right, so again, that's a horizontal line. We have to slice it vertically. That's going to be a perpendicular. We are going to have not just a void in our slice, but notice there's a space between where the curve even starts and the axis. So this one's going to have a hole all the way through it, like a napkin ring or some kind of like blood pressure cuff. There's going to be a hole right there. But there still is a void. So let's go ahead and draw our two radii. From the axis, which is now 2, to the first curve is little r. And from the axis to the second curve is big R. You always go to the axis, whether it's above or below, and you draw a line then to your curve. So here we go. We got it now. Volume is what goes in front? Pi. The sum of the infinitely thin slices from x equals 0 to x equals 1. Beefy brown bracket. Big R squared minus little r squared. Close beefy bracket dx. And then we come back with blue. We'll do blue. What is big R? Top minus bottom. Axis minus curve. 2 minus x squared. Quantity squared. And then lil r, 2 minus x. Yeah. There it is. Check, check. Fun. That would probably be a calculator question, but if it weren't, you'd have to expand out both terms, distribute the negative, power rule the heck out of it. All right, questions on B. Maybe we got time for one more? A, B, C comes next. Let's do it. The line y equals -5. Holy moly, smokers. That's way down here. Y equals -5. That's still a horizontal line, so we still have to slice it vertically, so it's still the perpendicular. And yes, this is a gigantic hole. This would be like a huge napkin ring for like maybe not a napkin, but maybe like a comforter or something. Yeah, there you go. So from the axis to the first curve is little r. From the axis to the second curve is big R. So the volume is going to be what goes out front? Pi. Sum of the infinitely thin slices from x equals 0 to x equals 1. Beefy blue bracket. Big R squared minus little r squared. Close beefy blue bracket dx. And now big R is top minus bottom. So in this case, it's curve minus axis. So it's x minus -5. What's x minus -5? X plus 5. And that's fine. And then little r is x squared minus -5, which is x squared plus 5. Check, check. Perfect timing. All right. Have a great rest of your day. And we'll see you next time. Stay mathy until then.